Far beyond the edge of our solar system, deep in the constellation of Leo, something extraordinary has emerged. A world, orbiting a distant red dwarf star, has sent a whisper through the darkness, a chemical signature hidden in the light. That signal, captured by the James Webb Space Telescope, has changed everything. It is not science fiction. It is not wishful thinking. It is real. In the quiet of a Cambridge morning, as data streamed across a computer screen, a pattern appeared that should not have been there. A signal that could only mean one thing: life. 120 light-years away, under skies no human has ever seen, something is breathing. The light that carries this revelation began its journey long before we were born. It traveled across the cosmic void, untouched, unbent, unbroken, until it met the golden mirrors of the most powerful observatory ever built by human hands. What it revealed was not just a planet. It was a message written in molecules and temperature, in chemistry and equilibrium. A message that said, "You are not alone." The planet is called K218b. To the untrained ear, the name might sound cold, distant, technical. But this world, orbiting a small red dwarf star in the constellation Leo, may be the most important discovery in the history of astronomy. Located 120 light-years away, K218b belongs to a class of planets known as super-Earths, worlds larger than our own, but smaller than gas giants like Neptune. For decades, scientists believed these planets were too massive, too volatile, too alien to support life. K218b has shattered that belief. K218b is more than 8 times the mass of Earth. Its surface gravity is nearly 3 times stronger. A person weighing 150 pounds on Earth would weigh over 400 pounds there. And yet, this intense gravity may be exactly what allowed the planet to hold on to its atmosphere over billions of years. While Mars lost its air to the cold vacuum of space, K218b's gravity holds its thick hydrogen-rich atmosphere in place like a protective shell. This atmosphere is not only stable, it is warm, rich, and potentially alive. What makes K218b extraordinary is not just its size, but its location. The planet orbits within what astronomers call the habitable zone, the distance from its star where temperatures are just right for liquid water to exist. But its star is not like our Sun. It is a red dwarf, smaller, dimmer, and far more stable. These stars burn slowly and steadily for trillions of years, far longer than the lifespan of our own star. For any planet in their orbit, this means an almost eternal window of time for life to begin, grow, and flourish without interruption. Despite orbiting so close to its star, completing one full orbit in just 33 Earth days, the planet receives nearly the same amount of energy per square meter as Earth does from the Sun. This is a cosmic coincidence, one that results in a planetary surface temperature of approximately 120 degrees Fahrenheit. That is the temperature of a hot summer day, the warmth of a fevered human body. And on K218b, that warmth is consistent, thanks to a dense hydrogen atmosphere that traps and redistributes heat across the entire globe, even on its night side. K218b is believed to be covered in a vast ocean, potentially hundreds of miles deep. This is not a planet of continents and deserts. It is a world of water. Beneath that water lies even more mystery, a deep interior potentially made of exotic forms of ice and compressed materials unlike anything found on Earth. The ocean may be enriched with dissolved hydrogen, forming a strange but stable environment where life could thrive in ways we have never seen. If life exists there, it may be swimming through waters deeper than our imagination, bathed in warmth and shielded by the atmosphere above. This is not Earth's twin. It is something far stranger and perhaps far more promising. K218b challenges our deepest assumptions about habitability. It shows us that life might not require an Earth-like planet, or an oxygen-filled sky, or even land to stand on. It suggests that habitability is not rare, it is diverse. The cosmos may be full of worlds like this one, each offering their own recipe for life. And in the hydrogen-wrapped skies of K218b, we may have just discovered the first proof that Earth is not the only place where biology has taken root. The atmosphere of a planet is more than just a blanket of gas. It is a record of everything happening below and above, an archive of chemistry, heat, light, and time. On Earth, our atmosphere bears the fingerprints of life: oxygen from photosynthesis, carbon dioxide from respiration, methane from decay, and water vapor from the endless cycle of evaporation and rain. Every breath we take is part of a living exchange. And now, light from a distant planet has revealed something eerily familiar. K218b does not just have an atmosphere, it has a breath. Using the unparalleled sensitivity of the James Webb Space Telescope, scientists peered through K218b's atmosphere as the planet passed in front of its star. With each transit, starlight filtered through the gases above the planet's surface, and hidden in that light were chemical signatures. First came water vapor, then methane, then carbon dioxide. But the most shocking of all was dimethyl sulfide, a molecule that, on Earth, is produced exclusively by living organisms. In that alien atmosphere, the unmistakable scent of life had drifted across the stars. Dimethyl sulfide, or DMS, is not a common molecule. On Earth, it is made primarily by marine phytoplankton, microscopic organisms that live in the ocean's sunlit layers. As they metabolize nutrients, they release DMS into the air. There, it plays a surprising role in cloud formation and climate regulation. But outside of biology, DMS does not appear. No known geological or chemical process creates it. That makes its presence on K218b not just curious, but extraordinary. It is as if a neon sign had been lit across the sky, flashing the word life. The detection was not a mere trace. The concentration of DMS in the planet's atmosphere was significant, strong enough to be observed across 120 light years. In science, such clarity is rare. The probability of the signal being a mistake, a false reading, or noise from the telescope was calculated to be less than 3 in 1,000. In the language of science, that translates to a confidence level of 99.7%. Not certainty, but astonishingly close. For astronomers, it was a discovery so profound that it made hands tremble and voices falter. But DMS was only part of the picture. K218b's atmosphere contains a mix of gases that, taken together, reveals something deeper, a system out of chemical balance. In a lifeless world, atmospheric gases eventually reach equilibrium, stable ratios dictated by physics and chemistry alone. But on a living planet, those ratios are in constant flux, pushed and pulled by metabolism, decay, respiration, and growth. The presence of methane alongside carbon dioxide in such abundance suggests a planet with ongoing biological activity, a world that is not just habitable, but inhabited. Even more intriguing is what is missing. One molecule that should be there, but is not, is ammonia. On gas giants and lifeless planets, ammonia often dominates the chemical landscape. It is produced by internal chemistry and should persist unless something removes it. On K218b, ammonia levels are surprisingly low. The likely explanation is biological removal. Some organism may be consuming it, breaking it down, using it as fuel or resource. That absence, like a missing piece in a puzzle, says as much as any presence. Life, it seems, edits its own atmosphere. Taken together, these atmospheric clues point to a single conclusion. K218b is not silent. It is not inert. Its air is being shaped, transformed, and replenished. It breathes. The gases rise and fall not just with seasons and storms, but with cycles of life. We are witnessing, for the first time in human history, the breath of an alien biosphere. It may be unlike anything on Earth. Its organisms may be built on hydrogen rather than oxygen. But the pattern is clear. The planet is alive, not metaphorically, but chemically, biologically, undeniably alive. When we imagine a star that can sustain life, we often picture something like our sun, bright, yellow, and familiar. But in the great theater of the cosmos, our sun is not the standard. It is unusual. The vast majority of stars in the galaxy are smaller, dimmer, and cooler. They are red dwarfs, and they are everywhere. These tiny stars make up more than 3/4 of all the stars in the Milky Way. Though faint and unassuming, they may hold the key to understanding life in the universe. Because red dwarfs are not just common, they are enduring. A red dwarf burns its fuel with incredible efficiency. While our sun will shine for about 10 billion years, a red dwarf can last for trillions. That is longer than the current age of the universe. It means that any planet orbiting a red dwarf has the luxury of time to form oceans, time to evolve life, and time for that life to grow in complexity beyond anything we have imagined. These stars do not rush. They glow slowly, steadily, like cosmic candles meant to burn through eternity. For life, that slow burn may be the greatest gift of all. K2-18, the red dwarf that warms K2-18b, is cooler and less luminous than our Sun. But it offers its planet something profound: stability. While more massive stars flare violently, exhausting their fuel in brief, brilliant lifetimes, red dwarfs like K2-18 maintain a gentle output of energy for unimaginable spans of time. That stability gives planets like K2-18b the opportunity to remain in the habitable zone not for millions, but for billions, even trillions of years. It is the kind of cosmic calm in which life can patiently take root. Red dwarfs have their own challenges. In their youth, they are known for intense stellar flares, violent outbursts of radiation that can strip the atmospheres from nearby planets. But once they mature, many red dwarfs settle into long periods of quiet stability. K2-18 appears to be one such star. Its flare activity is minimal, its behavior almost sedate. This quiet temperament means that its planet, K2-18b, is likely spared from the atmospheric erosion that dooms many other worlds. It has endured the tantrums of its star and emerged with its atmosphere intact. Because red dwarfs are cooler, their habitable zones are much closer in. A planet like K2-18b must orbit much nearer to its star than Earth orbits the Sun. This creates a phenomenon called tidal locking, where one side of the planet always faces the star, basking in perpetual daylight, while the other remains forever in darkness. At first glance, this seems catastrophic, a world divided into burning day and frozen night. But K2-18b's thick hydrogen-rich atmosphere solves the problem. It redistributes heat so efficiently that the entire planet remains warm and stable. The result is extraordinary. A planet with a permanent day side and a permanent night side, yet with global temperatures that support liquid water. There are no harsh winters, no shifting seasons, just balance. Life, if it exists there, would grow in a world of near constant warmth and stability. And that balance is made possible by the star itself. K2-18's quiet red glow does not scorch or freeze. It nurtures. It is a furnace that burns low and long, offering a kind of cosmic serenity. A different rhythm of time, perfectly suited for the evolution of life. In a universe dominated by red dwarfs, the discovery of life around one such star changes everything. It means that life may not be rare and fleeting, tied to brief windows around massive stars like our Sun. Instead, it may be long-lasting and widespread, nurtured by stars that live for eons. Red dwarfs may not look like much. Their light is faint. Their color is dull. But they are builders of time and holders of promise. They offer a stable foundation for the story of life to unfold, not in decades or centuries, but in cosmic chapters written over trillions of years. When we think of breathable air, we think of oxygen. When we think of planetary skies, we imagine nitrogen and carbon dioxide, clouds of water vapor, and winds moving through familiar elements. But on K2-18b, the atmosphere tells a different story. It is not made of what we breathe. It is not like Earth's. Instead, it is dominated by hydrogen, a gas that on Earth is rare and weightless, almost forgotten. Yet here, hydrogen is everything. It blankets the planet like a vast invisible ocean, creating a world that is alien, and yet surprisingly perfect for life. Hydrogen is the lightest element in the universe. It slips through fingers, rises into the upper reaches of atmospheres, and escapes into space with ease. On Earth, it makes up less than 1 part per million of the air we breathe. But on K2-18b, hydrogen is abundant. It forms the thick, extended shroud that envelopes the planet. This is not an accidental feature. It is a product of the planet's gravity, a pull strong enough to hold on to even the most elusive of gases. That alone makes the planet unusual. But what hydrogen does to the environment is nothing short of astonishing. Instead of acting as a volatile gas, hydrogen on K2-18b becomes a stabilizing force. It traps heat like a perfect greenhouse, not in the way carbon dioxide warms Earth, but in a deeper, more uniform fashion. The hydrogen-rich atmosphere redistributes stellar energy with remarkable efficiency. The planet's day side and night side, despite never exchanging light, maintain nearly the same temperature. There are no icy nights or searing days. There is only balance, an equilibrium born from hydrogen's ability to smooth the thermal extremes of a tidally locked world. This balance creates something incredibly rare in the cosmos, a planet where temperature does not vary wildly across space or time. Instead of experiencing scorching deserts and frozen poles, K2-18b offers its surface a warm, consistent environment. That warmth, hovering around 120 degrees Fahrenheit, is maintained by the thick hydrogen shell. It is warm enough for liquid water, yet cool enough to protect the integrity of organic molecules. And it is not temporary. With hydrogen holding the heat in, the planet's climate remains steady for billions of years. But hydrogen does more than insulate. It transforms chemistry itself. In the presence of hydrogen, elements behave differently. Carbon forms methane. Sulfur joins to create dimethyl sulfide. Complex molecules arise that on Earth require life to sustain them. Hydrogen encourages chemical reactions that mimic metabolism. In laboratory settings, scientists have found that hydrogen-rich atmospheres can facilitate the building blocks of life. On K2-18b, those processes may be happening on a planetary scale. The atmosphere is not just a blanket, it is a reactor, humming quietly with possibilities. To us, such an atmosphere would be unbreathable. We would suffocate in the absence of oxygen. But life, as it may exist on K2-18b, would see things differently. It might draw energy not from combustion, but from reduction, not from oxygen, but from hydrogen itself. Microorganisms on Earth that use hydrogen to live, found in deep-sea vents and underground aquifers, are primitive echoes of what may thrive in hydrogen-rich skies. Evolution, given time, might sculpt these simple forms into complex ecosystems, built not on blue skies and oxygen, but on clouds of invisible gas. This hydrogen world invites us to abandon our assumptions. We once thought oxygen was essential, that Earth-like conditions were a requirement for life. But K2-18b challenges that notion. It shows us that life may arise in places we never imagined. It may breathe air we cannot breathe, build chemistry we do not understand, and thrive in conditions that seem hostile only to us. The hydrogen atmosphere of K2-18b is not a barrier to life. It may be its foundation. And in this strange paradise, biology may have found a home more stable, more protective, and more enduring than Earth itself. Beneath the thick hydrogen atmosphere of K2-18b lies something that defies comparison to anything in our solar system. An ocean not merely of water, but of water laced with hydrogen, stretching for hundreds of miles in depth. This is not an ocean broken by continents or islands. It is a continuous, alien sea wrapped around the entire planet, deeper and darker than any abyss known to Earth. It is not only vast, it is ancient. And within its layers, something extraordinary may be unfolding. Life, thriving in a chemistry and pressure regime we have never seen. On Earth, the deepest parts of our oceans exert pressures that would crush most forms of life. But even there, we find creatures, blind, bioluminescent, surviving in pockets of geothermal heat. On K2-18b, the pressure at the bottom of the ocean is far greater, perhaps thousands of times stronger. But the hydrogen dissolved into the water may act as a buffer, stabilizing the liquid state and allowing complex chemistry to flourish. This is not just water. It is a dense, energy-rich medium that could provide nutrients, structure, and even respiration for unknown forms of life. In this hydrogen ocean, life would not breathe oxygen. It would not photosynthesize beneath a blue sky. It would feed on gradients of chemistry, on the slow reactions between dissolved gases, on the quiet dance of molecules under pressure. Some microbes on Earth already do this. They metabolize hydrogen, exhaling methane. In the hydrogen-rich sea of K2-18b, such metabolisms could become dominant, not rare. Entire biospheres may exist in the darkness, layered ecosystems where energy flows without sunlight, driven by reactions that Earth life only hints at. The vastness of the ocean changes everything. It is not a narrow band of life hugging the coasts. It is a full planetary volume, kilometers deep, a cradle where evolution can take its time. Temperature remains steady, protected from the flares of the star and the shifting skies. Currents may circulate slowly, carrying nutrients from the depths to the upper layers, just as Earth's ocean does. But here, the conditions have remained stable, not for millions of years, but perhaps for billions. That stability gives life the one thing it needs most: time. And what of the surface? The boundary where ocean meets atmosphere on K2-18b is likely shrouded in dense clouds, warm to 120 degrees Fahrenheit. There may be no waves, no shorelines, only the calm hiss of chemical exchange. Hydrogen from the air dissolving into the water, and water vapor rising back into the sky. It is a breathing cycle, one that supports a hidden world below. The ocean may exhale gases into the atmosphere, methane, dimethyl sulfide, leaving signs visible across the stars, signs that life is present, even if we cannot yet see its face. To imagine this ocean is to imagine a world built on unfamiliar principles. No sunlight dances on its surface, no birds fly above it. Yet, it may be the most life-friendly environment in the galaxy, a place where pressure and chemistry, heat and hydrogen combine to create a haven for biology. The discovery of such a sea changes how we think about life. It tells us that the universe is not limited by Earth's examples. It can sculpt living worlds in places we once considered impossible. And in the silence beneath a hydrogen sky, life may be speaking in molecules we have only just begun to understand. In the search for life beyond Earth, scientists do not look for creatures, or cities, or footprints in the dust. They look for imbalance, for signs that a planet's chemistry is not behaving as it should. On lifeless worlds, chemistry reaches a kind of quiet equilibrium. Gases mix and react, then settle into stable patterns dictated by physics alone. But on a living world, equilibrium is disturbed. Molecules that should not coexist linger side by side. They are replenished, renewed, reshaped by processes that defy chemistry's natural endpoint. This is the signature of life. Not silence, but disruption. K218b is a planet out of balance. Its atmosphere contains water vapor, carbon dioxide, methane, and most surprisingly, dimethyl sulfide. Each of these molecules, on its own, can be explained by simple geochemical processes. But together, in these quantities, their coexistence becomes difficult to justify without invoking life. Methane should break down in the presence of ultraviolet radiation. Dimethyl sulfide should vanish quickly unless continuously produced. Yet both remain. Their presence signals that something is pushing against chemical stability, something active, persistent, and alive. This idea, chemical disequilibrium as a marker for life, comes directly from Earth. Our atmosphere is a masterpiece of imbalance. Oxygen, a highly reactive gas, exists in abundance because plants are constantly producing it. Methane, which should be destroyed by sunlight, persists because microbes keep releasing it. The only way this imbalance can exist is through the breath of a biosphere. When astronomers saw the same type of imbalance on K218b, they knew it could not be ignored. It was not just an atmosphere, it was a message, a chemical whisper from a living world. The presence of dimethyl sulfide carries special weight. On Earth, no non-biological process has ever been found to create it in significant quantities. It is made by life, specifically by oceanic plankton and certain bacteria. It plays a role in cloud formation, climate regulation, and even weather patterns. Its structure is complex enough to require enzymes, machinery that only cells know how to build. To detect this molecule on K218b is to detect the signature of a planetary metabolism, a chemical pattern that cannot be explained by rocks or storms, or volcanism alone. Even more powerful than what is present is what is missing. Ammonia, a molecule that should be abundant in a hydrogen-rich atmosphere, is curiously absent. On gas giants and lifeless exoplanets, ammonia often dominates. Its absence on K2-18b is not a fluke. It is a clue. One possible explanation is that ammonia is being consumed, broken down by biological processes, metabolized as food or fuel. Just as life on Earth reshapes its environment, life on this alien world may be sculpting the very air, removing what it does not need and exhaling what it does. This chemical choreography is not random. It is structured, self-sustaining, and dynamic. Models of K2-18b's atmosphere show layers of gases interacting in complex cycles, cycles that are hard to maintain without an active biological engine underneath. Just like Earth's carbon cycle or nitrogen cycle, these processes may be running on loops of consumption and release, conversion and renewal. The patterns of imbalance repeat across time, like the pulse of a living system. And just as our breath changes the air around us, something on K2-18b may be breathing too. The biosignatures on K2-18b are not final proof, but they are a doorway. They mark the strongest evidence yet that life exists beyond Earth, not in myth or speculation, but in the hard numbers of spectroscopy. The disequilibrium in its skies is not an error. It is a rhythm. And that rhythm tells a story of chemical defiance, of a planet that refuses to settle, of molecules that rebel against stillness. It is a story of life. Hidden beneath clouds of hydrogen, echoed in the chemistry of the air, and written across the light that traveled 120 years to reach us. Floating nearly 1 million miles from Earth, far beyond the pull of the Moon and the shadow of our own planet, the James Webb Space Telescope orbits a point of perfect gravitational balance. It exists in silence, in darkness, suspended at what astronomers call Lagrange Point 2. From this perch, the telescope stares into the depths of time itself. Shielded from the sun's heat and Earth's light, it sees the universe not in visible colors, but in a wavelength invisible to human eyes. Infrared. It is the heat of planets, the breath of atmospheres, the glow of stars long gone. Webb's mirror is a marvel of engineering. It stretches over 21 feet across, composed of 18 hexagonal segments, each crafted from beryllium and coated in a whisper-thin layer of gold. These mirrors work together like a single, perfectly curved surface, aligned with precision so exact that a misalignment smaller than the width of a human hair would render the image useless. Together, they focus light with such sensitivity that Webb can detect the heat signature of a bumblebee on the Moon, or the molecular breath of a planet 120 light-years away. But size is only part of the miracle. What makes Webb revolutionary is its ability to analyze light that has traveled across unimaginable distances and extract from it the fingerprints of molecules, When a planet passes in front of its star, a tiny sliver of starlight filters through the planet's atmosphere. Different molecules absorb specific wavelengths of that light, creating patterns, spectral lines, that reveal their identity. This is how we know K218b has water vapor, methane, carbon dioxide, and dimethyl sulfide. These patterns are not guesses, they are measurements. To detect these spectral fingerprints, Webb uses instruments cooled to just a few degrees above absolute zero. Its sun shield, a 5-layer membrane the size of a tennis court, blocks heat from the sun and Earth. Behind this shield, the telescope lives in eternal night. Every photon it collects is precious. Some of these photons began their journey when Theodore Roosevelt was president. Others have traveled since before World War I. Each one carries with it the story of a distant world, and Webb's instruments translate that story into the language of science. One of Webb's most powerful tools is its coronagraph, a technology that allows it to block out the overwhelming glare of a star and see the faint light of a planet orbiting beside it. It is like using a thumbnail to eclipse the sun and suddenly seeing a firefly hovering nearby. The contrast is staggering. A planet like K218b is billions of times fainter than its host star. Yet Webb, using a combination of precision optics and image processing, isolates the planet's light and examines it. In that dim glow, it finds signs of life. The data that Webb collects is not simple. It arrives in raw, fragmented pieces, spectral curves, temperature profiles, light curves measured over hours and days. To extract meaning from this data, astronomers rely on some of the most advanced algorithms ever created. Artificial intelligence sifts through millions of numbers, separating noise from signal, distinguishing a real molecule from a cosmic illusion. When scientists announced the detection of dimethyl sulfide, it was not based on a single moment of discovery. It was months of observations, cross-checked and confirmed again and again. Science rarely speaks in absolutes. It speaks in probabilities, in margins of error, in confidence levels. Certainty in the scientific world is earned through rigor, not declared through belief. When astronomers announced that dimethyl sulfide had been detected in the atmosphere of K218b, they did not say, "Life exists." They said, "We are 99.7% certain." That number may sound modest to some, but in the language of science, it is nearly a shout. It is the same level of confidence used to declare the discovery of new particles and gravitational waves. To understand what this means, imagine flipping a coin 1,000 times and getting heads 997 times. The odds of that happening by chance are almost non-existent. In statistical terms, this level of certainty is known as a 3 sigma detection. It means that the signal detected is real, not a fluke, with only a 3 in 10,000 chance that it is an error. Scientists are trained to be skeptical. They look for alternative explanations, for instrumental noise, for contamination from Earth. But in this case, every other explanation has been tested and ruled out. Multiple independent observations were made using different instruments on the James Webb Space Telescope. Each one confirmed the same spectral signature, the same molecule, the same atmospheric imbalance. This is not the result of one lucky measurement. It is the outcome of repeated experiments, months of data, and analysis that has been scrutinized by scientists around the world. The statistical weight behind the conclusion makes it one of the most significant discoveries in the history of exoplanet science. It moves the idea of alien life from speculation into the realm of evidence. The precision required to reach this level of certainty is staggering. To detect dimethyl sulfide, Webb had to measure the absorption of light at specific infrared wavelengths to an accuracy of 1 part in 10 million. It is like measuring the width of a human hair with the precision of a single atom. This is what makes the 99.7% figure so powerful. It is not based on guesswork or interpretation. It is based on numbers, on the measured interaction between starlight and molecules in an alien sky across 120 light-years of empty space. In a world full of uncertainty, this kind of clarity is rare. And while science will always leave room for doubt, this discovery has crossed a threshold. It has moved from possibility to probability, from hope to high confidence. The atmosphere of K2-18b is not a random mix of gases. It is a structured, dynamic system, altered by processes that most likely include life. And when the numbers speak this clearly, we must listen, not with blind faith, but with open eyes, understanding that we are standing on the edge of something profound. We are close, closer than ever before. The James Webb Space Telescope is more than a machine. It is an extension of human curiosity, a mirror not only for the stars, but for ourselves. It reflects what we are willing to build in order to answer the oldest question: are we alone? In the golden petals of its mirror and the frozen silence of its sensors, we have built a kind of truth detector. And in the skies of K2-18b, that truth is beginning to speak. Not with words or pictures, but with molecules, with warmth, with imbalance, with breath. We are watching another world exhale. For centuries, we have looked at the night sky and seen only silence. The stars seemed cold, distant, unreachable. The cosmos was vast but empty, a backdrop for human drama, but not a participant in it. We believed ourselves to be alone, not by proof, but by absence. No voice had answered, no message had arrived. In this stillness, we built our philosophies, our religions, our sciences. And yet, even in our solitude, we always wondered, what if the silence was not emptiness, but waiting? What if the universe was not dead, but sleeping? Or better yet, what if it was alive? The discovery of life on a distant world is not merely a scientific event. It is a transformation of perspective. If K2-18b truly breathes with biology, if its skies carry the exhalations of unseen organisms, then we must accept that life is not a miracle confined to Earth. It is a property of matter itself, a tendency of the cosmos to awaken. Just as gravity shapes stars and time bends near black holes, life too may be a natural consequence of the universe unfolding. It may be what the universe does when it gets the chance, when conditions are right, when chemistry has time to become consciousness. This shifts everything. It reshapes how we define existence. Earth is no longer the cradle of all meaning, but one chapter in a longer story. Humanity is no longer an isolated flame in the dark, but one flicker among many. To realize that we are not alone is to see the universe not as a cold machine, but as a living web of potential. Other minds may exist, different, distant, perhaps unknowable, but present. In that presence lies kinship, not competition, connection, not fear. And from that connection comes humility, for we are not the center, but participants in a cosmic ecology of life. There is something deeply human about looking outward to find ourselves. In the reflection of alien oceans, we may better understand the fragility of our own. In the breath of a distant biosphere, we may rediscover the value of our atmosphere. Life beyond Earth does not diminish our importance. It enriches it. It reminds us that existence is not rare, but precious. That survival is not a guarantee, but a privilege, and that intelligence, no matter where it arises, carries the burden of care for its world, for its neighbors, and perhaps one day, for the galaxy it inhabits. When the universe breathes, it tells us something we have always suspected in our deepest myths and dreams, that we belong to something greater, that the same forces which forged the stars have also forged the spark within us. We are not alone. We were never alone. The silence was never absence, it was distance. And now that light and time have bridged that distance, we must be ready not only to listen, but to understand. Because when the cosmos speaks through the chemistry of a distant sky, it does not speak in words, it speaks in wonder. For generations, the dream of finding life beyond Earth was centered on a single goal: discovering another Earth. A rocky planet with oceans and blue skies, circling a sun-like star at just the right distance. But that idea was shaped by our own reflection. We searched for ourselves in the stars. Now, K218b and planets like it are teaching us a deeper truth. Life does not need a mirror image of Earth. It only needs stability, chemistry, and time. And those conditions, it turns out, are not rare. They may be woven into the very fabric of the galaxy. Within a radius of 200 light-years, astronomers have already identified dozens of planets that exist within the habitable zones of their stars. Some orbit red dwarfs, others encircle stars brighter than our Sun. Some are smaller than Earth, others are vast ocean worlds, with atmospheres rich in hydrogen or methane. Each one is a different experiment in planetary evolution, a unique configuration of pressure, light, and chemistry. And if even a handful of them harbor life, then the galaxy may be home not to a few living worlds, but to billions. This changes the way we understand biology itself. Life may not be an exception to the rules of the universe. It may be one of its most common expressions. Just as stars form when gravity compresses gas, life may arise when molecules find warmth, water, and shelter. It may be inevitable. In that case, the Milky Way is not a vast emptiness scattered with rare oases. It is a garden, a network of living worlds, each shaped by its own history, its own light, its own possibilities. K218b is not alone, and neither are we. With each discovery, our map of the living universe grows. Biosignatures, molecules like oxygen, methane, dimethyl sulfide, are no longer just chemical curiosities. They are evidence, they are beacons, and they suggest that life does not hide in the corners of the cosmos. It announces itself in atmospheres, in cycles of imbalance, in heat that persists beyond reason. The James Webb Space Telescope was not just built to look at planets, it was built to listen. And what it hears is a chorus of worlds, each breathing in its own language. To imagine a network of living worlds is to imagine a galaxy alive with purpose. Not one shaped solely by stars and gravity, but by biology and time. Life may not be the rare flower in a desert. It may be the grass between the stars. If this is true, then the next question is not whether life exists elsewhere, but what form it takes, how it thinks, and whether it too wonders if it is alone. The answer, carried in molecules and light, is gently arriving. We are not just discovering new planets, we are discovering neighbors. The James Webb Space Telescope has opened the door, but it is only the beginning. The next chapter in our search for life will not come by accident. It will be designed, engineered by minds who dare to imagine instruments capable of touching the distant breath of a world. Future telescopes will go beyond what Webb can do. They will not just analyze light that passes through atmospheres. They will capture direct images of alien planets, resolve continents, oceans, weather systems, perhaps even artificial structures. The technology is already being planned. The future is being built. One such mission is the Habitable Worlds Observatory, a space telescope designed to observe Earth-like planets around nearby stars with far greater resolution than ever before. It will use advanced coronagraphs or even star shades, immense flower-shaped screens that block out a star's glare to reveal the planets circling it. These tools will allow us to study dozens of worlds in exquisite detail. We will not just detect the presence of water or methane. We will begin to understand climate systems, seasonal changes, and maybe even surface biology. We will move from detection to observation. But it will not stop with telescopes. In the decades ahead, we may launch interstellar probes. Projects like Breakthrough Starshot envision tiny spacecraft traveling at a significant fraction of the speed of light, propelled by powerful laser arrays on Earth. These probes, no larger than a postage stamp, could reach nearby star systems within a human lifetime. They would send back data, images, spectra, magnetic fields from worlds we have only imagined. It would be our first physical contact with the stars, our first step into becoming an interstellar species. Artificial intelligence will also play a central role. As data from future observatories floods in, AI systems will sift through millions of signals, looking for patterns too subtle for the human eye. These systems will learn to recognize the fingerprints of life, the anomalies that hint at civilization, the whispers of unknown chemistry. They will be our ears in the cosmos, our logic extended into the stars. And with each new detection, they will become smarter, more precise, more relentless. The search will accelerate, guided not only by wonder, but by learning machines. What lies ahead is not a single moment of discovery, but a long unfolding, a journey of patience, technology, and hope. We may never receive a message, we may never meet another intelligence face to face, but through light, through chemistry, through careful observation, we will come to know that we are part of something vast. The tools we build today will shape the answers of tomorrow. And in those answers, we may finally glimpse not just the structure of the universe, but its meaning. There is a moment, quiet and personal, when the mind finally accepts what the evidence has been trying to say. It is not the result of a press release or a scientific paper. It happens in silence, often when looking up at the night sky. You realize that the data is not just numbers. The molecules are not just chemistry. This is not a theory. This is a presence. Somewhere, across a gulf of time and space, something is breathing. Something is living. And for the first time in the long history of our species, we know we are not alone. That realization does not arrive like a thunderclap. It settles slowly, like dawn breaking through the darkness. The loneliness that has shaped so much of human imagination begins to dissolve. We are no longer the only island of life in a sea of stars. We are part of a network, a community not yet seen, but real. The silence of the cosmos was never rejection. It was distance. And that distance has finally been crossed, not by ships or signals, but by light, by the quiet truth carried in the atmosphere of an invisible planet, a truth now written into the story of us. This moment will not change the world overnight, but it will change everything in time. It will reshape our place in the cosmos and our responsibilities within it. We are no longer children in the dark, wondering if anyone else is out there. We are witnesses to a universe that grows more alive the deeper we look. In the chemistry of a faraway sky, we have found our mirror, not of flesh or form, but of breath and being. And in that mirror, we no longer see solitude, we see kinship. Across the vastness of space, where silence has reigned for billions of years, something has shifted. Not a voice, not a signal, but a breath. The delicate presence of molecules that should not coexist, the rhythmic imbalance of gases, the echo of life processes sustained across alien skies. These are not accidents. They are patterns, intentional, continuous, alive. For the first time in history, the human species has looked into the dark and seen not emptiness, but expression. The universe is no longer still. It is speaking. It is alive. To say the universe is alive is not poetry. It is not metaphor. It is observation. It is the recognition that life, however rare, however fragile, is part of the fabric of the cosmos. It emerges from it, shaped by its laws, nurtured by its light. A living universe is not one filled only with biology. It is one where matter and consciousness are not separate things, but different expressions of the same origin. In that vision, we are not anomalies. We are inevitabilities. We are what the universe does when it has time and potential. And so we arrive at a turning point, not of technology, but of identity. We have built telescopes, launched missions, measured molecules, but in doing so, we have also rewritten our place in the cosmos. We are no longer the only known spark of awareness. We are not the first breath, nor the final voice. Others may have come before. Others may still rise after us. The living universe is not about us alone. It is about the shared potential of all things that rise from star stuff and look back toward the stars. This new understanding carries a quiet urgency. If life is not rare, then it is also not guaranteed. If the universe nurtures life, it can also take it away. And so the living universe becomes a responsibility to explore with care, to search with humility, to preserve what we have, not just for ourselves, but as part of something greater. The moment we knew we were not alone was not just a scientific milestone. It was a moral awakening, a reminder that the breath of one world may one day depend on the choices made by another. In the end, the cosmos remains immense, mysterious, and silent in most places. But it is not dead. It is awakening. From hydrogen clouds to conscious thought, from planets unknown to signals unseen, the universe is not just a container for life. It is life in its most expansive and cosmic form. And now, as we gaze into that truth, we carry with us the knowledge that we are part of a living story. One that began long before us, and one that, if we are careful, curious, and kind, will continue long after. If you enjoyed this video, please give it a like and subscribe to our channel. Let us know your thoughts in the comments. We'd love to hear from you. Thanks for watching, and we'll see you in the next one.